Uh, Fine, let us start now. Good evening, everyone. Myself Shankar Rao, a PhD scholar in the Department of Electrical Engineering, IIT Hyderabad. So, as it was already put in the website, that today's session will be on network systems. So, we will take some of the previous problems, previous year question papers, questions from previous year question papers, and we will try to solve those problems by learning the related concepts and all. Also, yeah, there may be actually some trivial problems may be there. Because these were assigned for me, so those things I will be solving now. Maybe some may be tricky questions, some may be trivial problems. Fine. So this is the first question that we are going to solve now. This is given in GATE 2015 ECE set 1 for 1 mark. So the question is, in the circuit shown at resonance, the amplitude of this sinusoidal voltage across the capacitor is. So the circuit given is a series RLC circuit. So at resonance, we need to find out the voltage across the capacitor. Its amplitude we need to find out. Okay. So first let us understand about the resonance, and then we'll solve this problem. So let us say we consider a series RLC circuit in phasor form. I'm considering. So we have a resistance, an inductor, and a capacitor. We have some voltage source connected here. So voltage source. This phasor form, let us say V at some phi. So just V I'm saying. So this is VR, this is resistor, and this is VL, inductor, and this is capacitor. Let us say we see these are the, and they, since these are in series, so the current through all the elements is common, that is I. So this is a typical series RLC circuit. Okay, now in this, what is the impedance? So the impedance in this is ZR plus ZL plus ZC, all they are in series. So here ZR means R, ZL is J omega L plus ZC is 1 by J omega C. Now this I can write like R plus J into omega L minus 1 by omega C. So this is the impedance of the circuit. This impedance is a function of frequency. If you can see here, this impedance is a function of frequency. Now if I draw a plot between frequency and this impedance, so here R is some constant here. How the impedance of inductor resistor they varies. R is some constant based on the resistance, and impedance of the inductor is omega L. So it's some linear with respect to uh, this one frequency, and impedance of the capacitor is 1 by omega C. It is something like this. So somewhere here the impedance of the inductor, this is impedance of the capacitor, So somewhere here the impedance of the inductor and impedance of the capacitor both equal. That is called, let us say, some frequency omega naught. If you see below omega naught, for frequencies lesser the omega naught, the impedance of capacitor is more compared to impedance of inductor. So here we will have capacitive dominance will be there. The circuit is capacitive, and above omega naught we have impedance of inductor is more, you can see here. So here the circuit is inductive, and at omega naught what will happen, impedance of at omega naught impedance of inductor is equal to impedance of capacitor. That is what impedance of inductor is omega naught L and impedance of capacitor is omega naught C. If we see here in Z, here in Z, impedance of inductor, impedance of capacitor will get cancelled. So only we will get R. So at omega naught the circuit is resistive. Okay. At omega naught the circuit is resistive. So if we can see here at this omega equal to omega naught, so here the impedance of inductor is equal to impedance of capacitor. That implies from here omega naught equal to 1 by root LC. So at omega naught equal to 1 by root LC, so impedance of inductor and impedance of capacitor will become equal. Then the resultant impedance will become only R. The imaginary part will become 0. So this will become 0 at omega naught. So the circuit purely acts as a resistive circuit. That is, the combination of inductor and capacitor combination acts as a short circuit. Okay. So at omega equal to omega naught, the combination acts as a short circuit. Okay. So Z of j omega naught equal to R at resonance at omega equal to omega naught, the overall impedance. Now what is the current in the circuit? The current in the circuit, since it is in series, we can say V by Z is the current. At resonance the current is V by Z equal to R, we know. So at resonance the current is in the circuit is V by R. Okay. So we have seen this already. At resonance ZC plus ZL equal to 0. At resonance ZC plus, this is ZC means J minus J by omega C plus J omega L. So this will become 0. That means J into omega L minus 1 by omega C. This will become 0 since both are equal. And if I draw the impedance, magnitude of impedance, that is mod Z, with respect to omega, how it looks like. So we have impedance is what? Z of j omega is R plus J into omega C minus, sorry, omega L minus 1 by omega C. So mod Z is something like this, R square plus omega L minus 1 by omega C square. So we will get something like this. If you draw the impedance of the series RLC circuit, we will get something like this. So at omega equal to omega naught, at resonance we will get the lowest impedance. Impedance is the lowest, least, that equal to R. That means here we will have maximum current through the all the elements. Okay. Now what are the voltages at resonance? At resonance, now we will see at resonance what are the voltages across capacitor, inductor and resistance. So we have seen since we have already I equal to V by R, this we have got here. I equal to V by Z, but Z is R, that's why I equal to V by R, that's the series voltage, sorry, series current. Now the voltage across resistance is what? I into R, so V by R into R, so that equal to V. Voltage across resistance is V. Now voltage across inductor is J omega L, inductor impedance into I. So this is J omega L into I is V by R. This I can express like omega L by R. So this is at resonance, that's for omega equal to omega naught I am writing at resonance. That is at omega equal to omega naught. So into V, J I can express as 90 degrees. So this I can write like QV at an angle of 90 degrees. Okay, na? This Q is called quality factor of the series RLC circuit. Q factor we will say. Okay. Similarly, voltage at across the capacitor is 1 by J omega L into 1 by J omega C into I, that is minus J into 1 by omega C into V by R. This I can write like QV minus 90 degrees phase. So here the Q is here 1 by omega naught R C. Okay. Here Q is omega naught L by R. Okay. So this Q is called quality factor of series resonance RLC circuit. So Q I can write from VL what I got Q as omega naught L by R. From here it is 1 by omega naught RC. Actually there is another definition for Q. Uh, so the quality factor Q is defined as omega naught into maximum energy stored in the inductor or capacitor at resonance by average power dissipated. Actually, Q factor is defined like this for series RLC circuit or parallel RLC circuit. Omega naught, the resonant frequency, into maximum energy stored in the inductor or capacitor at resonance by average power dissipated at resonance. So omega naught into energy stored in the inductor, we can say half L I square, by average power dissipated is uh, Vrms square by R. We can say Vrms square, I can write some, this is the average power, but I we know, I we have Vm by R, maximum energy stored. I we have Vm by R. So this will get something like this, omega naught L by R, half Li square, right? So maximum current is when the voltage is maximum, that is Vm. Vm by R is the maximum current. Average power we know Vrms square by R. So omega naught L by R will get. If the same thing if I write for capacitor, we will get omega 1 by omega naught RC will get. So that's what I have written here. Instead of Q, instead of omega naught L by R, I am just writing Q. Okay, this is how Q we will derive. So at resonance, resistor voltage is same as voltage, input voltage. Inductor voltage is QV at 90 degrees and capacitor voltage is minus QV at 90 degrees. So the Q factor is omega naught L by R, that is 1 by omega naught RC, and also this we can write like omega naught, already we got 1 by root LC, right? Resonant frequency we have seen somewhere here. Yes, at omega naught, impedance of inductor, impedance of capacitor both are same. So this we got, right? Resonant frequency omega naught is 1 by root LC. If I replace here, instead of omega naught 1 by root LC, if I replace, what I get is Q as 1 by R root L by C. This is also Q. So we have three different forms of Q: omega naught L by R, 1 by omega naught RC, and 1 by R root L by C. This is about Q. Okay. Now we will see our, and at resonance, what are the voltages? At resonance, V is the voltage of resistance, and inductor voltage is QV at an angle of 90 degrees, and the capacitor voltage is minus QV at an angle of 90 degrees. These things we have seen. Now let us come back to our problem. If you see here, this is a series RLC circuit, and I will represent this in the form of phasor form. I hope you know about the phasor form. In AC, like sinusoid steady state analysis, in AC circuit analysis, what we do, instead of writing in this way, let us say something, we have Vm cos omega naught t uh, plus some phi we have. In phasor domain, this we will represent like this. Okay, while analysis, let us say in different textbooks follows different standard. So some textbooks may follow cos as reference, another textbook may follow sin as reference. I'm taking cos as reference. So let us say if you have some signal like this, Vm cos omega naught t plus phi, then this will represent the signal like this, Vm at an angle of phi. And let us say inductor, how will represent inductor? J omega naught L. At what frequency that is there, inductor will represent with this, and capacitor will represent with 1 by J omega naught C, and resistor same as resistance. In phasor domain, so that much phasor domain representation is not required for this problem, but still I'm writing this like this. So our circuit is, so cos 10 cos omega t, so I'm writing 10 at an angle of 0 degrees, omega t plus 0 degrees, right? So 10 at an angle of 0 degrees, this is 4 ohm. So inductance is j omega, some omega is given, j omega L 1.1 m. But anyway, phasor domain representation is not required for this. 1 microfarad. Fine. But in the question it is asked to find out the amplitude of the sinusoidal voltage across the capacitor at resonance. At resonance, we need to find out the amplitude of the sinusoidal voltage across the capacitor. So just now we have seen the voltage across the capacitor at resonance is Vc is minus Q V at an angle of 90 degrees. We have seen, right? Minus QV at an angle of 90 degrees. So what is Q? Q, three definitions we have seen: omega naught L by R, or 1 by omega naught RC, or else 1 by R root L by C. All these are different definitions of Q. So based on what values we have RLC we have, so 1 by R is 4, L is 0.1 milli Henry, and this is 1 into 10 power minus 6. So we get 10 by 4, 2.5 is the Q factor. Now what we get? VC, what we get? VC we get minus 2.5 V at an angle of 90 degrees. So minus, this is phasor representation. So minus 2.5 V is how much? 10 at an angle of 0 degree. So 10 at an angle of 0 degree, and we have already 90 degree here. So I can say minus 25 at an angle of 90 degrees. Okay. So this I can represent like minus 25 cos omega t plus 90 degrees. Okay. Minus also we can take inside. So this still I can represent 25 cos omega t, minus means 180 degrees, right? So it I can write 270 degrees. Okay. Anyway, VC we get like this. So the question what was asked is amplitude of the sinusoidal voltage across capacitor. This is the amplitude, right? Amplitude is 25. So answer for this is 25 volts. So is this okay? You can ask me now if you have any doubts from this. Understood, right? Any doubts? Okay, fine. So now we'll see another question. This question is given in same GATE 2015 ECE set 1 for 2 marks. Sorry, I think this is 2 marks only. The damping ratio of a series RLC circuit can be expressed as. So just now we have seen series RLC circuit. I'm not going into details here. So the damping ratio is zeta, represented by zeta, that is 1 by 2q. It is expressed as 1 by 2q. Okay, the relation between damping ratio and the quality factor is 1 by 2q. So 1 by 2, already q we have seen something like this, right? 1 by r root L by C already defined, uh, derived in the previous one, 1 by r root L by C. So we will get something like this, r by 2 C by L. This is the damping ratio. Okay. Uh, More details about this, the damping ratio, all these things you will study in control systems. Okay. So the behavior of a, like let us say RLC series or parallel RLC circuit will be studied under different conditions, like under damped system, critical damped system, over damped system. More details about this you will study there. Okay. So this you can remember, the damping ratio zeta is 1 by 2q. So for a series RLC circuit, q we have just now derived. So here C is the answer. So whatever we have done for a parallel series RLC circuit, the similar way you can solve for a parallel RLC circuit. Okay, whatever we have done, analysis we have done for a series RLC circuit, similar way you can solve for a parallel RLC circuit. Okay. The next question is, this question was given in GATE 2013 ECE set 1 for 2 marks. The question is, two magnetically coupled inductive coils have Q factors Q1 and Q2 at the chosen operating frequency. Their respective resistances are R1 and R2. When connected in series, their effective Q factor at the same operating frequency is. Okay. So here given two coils are given. That is, a coil means we will have practical coil will have some inductance and some series resistance. Okay, this is a coil. Inductance, let us say L1, and some series resistance R1. Okay, and another one, let us say L2 R2, second coil. Okay, now they are connected in series, and one more point we have to note down here, they are magnetically uncoupled. Okay, if they are coupled magnetically, then we will get a different equivalent inductance. So let us see those things. I think you might have studied these things as well. Suppose we have two coils, two inductors connected in series. Okay, two inductors, some L1 and L2. There is a mutual inductance between them, and here dot indicates the similar type of polarity regarding those coils. We will have some mutual inductance. Now if let us say some current is entering, okay, now in the both the coils, if the current enters in the both the coils or leaves in the both the coils from the dot, let us say here for the first coil the current is entering at dot and current is leaving entering at the dot for the second coil also, or in the both the coils the current is leaving at the dot. Okay, okay, here also current leaving, here also current leaving, that then they will aid actually, it is like aiding the magnetic coupling between them, or electrical magnetic coupling, the mutual inductance between them will aid. Okay, so the equivalent inductance is, since they are connected in series, L1 plus L2 plus 2 times of M. So L1, because this M is nothing but the mutual inductance between L1 and L2. So they'll become L1 plus M. Inductance of first coil is L1 plus the mutual inductance of L2 on L1, that is M. Similarly, inductance of second coil will become L2 plus M. So overall inductance will become L1 plus L2 plus 2M. Okay, when there is mutual inductance between them M. Suppose if in another case, if I'm telling at both the dots the current is entering or leaving at the both the dots. Suppose in another case, okay, at one dot current is entering and another dot current is leaving. The dot convention is like this. For the first one current is entering, second one the current is leaving. Then in this case inductance of, let us say M is the mutual inductance between them, then the overall inductance will be, equivalent inductance will be L1 plus L2, sorry, minus 2M. Here in this case it is magnetic aiding. Okay, here it is like subtracting L1 plus L2 minus 2M when there is a mutual inductance between them. While coming to our problem, here it is clearly said magnetically uncoupled. That means the mutual inductance is not there. Mutual inductance is not present between the coils. So for a single coil, what is the Q factor? We have already seen. Let us say Q1 is the Q factor. They are operating at some frequency omega naught. Some frequency omega naught. Let us say we have seen Q factor is omega naught L1 by R1 for the first coil, and for the second coil is Q factor is omega naught L2 by R2. Just now we have derived. from the series RLC circuit. Okay, Q factor for this omega naught L by R. For the second one, omega naught L2 by R2. Since they are in series, and L equivalent will become L1 plus L2 plus something like 2M. This 2M is not there because they are not coupled, magnetically not coupled. So since they are in series, so overall equivalent resistance will be R1 plus R2. So we need to find out Q factor for the equivalent circuit. We need to find out. Okay. Individual Q factors are Q1 and Q2. We need to find out Q for the equivalent circuit. So for the equivalent circuit, we can define Q factor as omega naught L equivalent by R equivalent. So omega naught into L equivalent is L1 plus L2 and R equivalent is R1 plus R2. But this option is not there. So little bit manipulation we need to do. We need to express in terms of Q1 and Q2. So I'm just writing omega naught L1 by R1 into R1 plus omega naught, numerator I'm writing like this, by R1 plus R2. So we have seen this is Q1 and this is Q2. So this is Q1 R1 plus Q2 R2 by R1 plus R2 Q equivalent. So C is the option C is the correct option. Q1 R2 Q1 R1 plus Q2 R2 by R1 plus R2. Is that okay? So we need to find out Q factors for individual ones, and there is we need to find out equivalent inductance and resistance. Since they are in series, they are adding up. There is no magnetical coupling is there. So from that we need to find out the overall Q factor. Is that okay? Oh, this topic is not in GATE syllabus. Maybe they might have removed now. I'm not sure. But this was like given in GATE 2013. But these things will come definitely, I guess. Maybe explicitly, okay, according to GATE 2023 syllabus, this is not there in the syllabus you're telling. Okay, okay, fine, fine. They may not in the syllabus, they may not clearly explicitly mentions like Q factor or coupling these things, but they may ask. But okay, that magnetic coupling and all may not be there, but this kind of question still they can ask, right? I hope series and parallel resonance is there in the syllabus, right? Series parallel RLC circuits, right? If that is there, then they may ask this kind of question also. Okay, okay, fine. Filters are network. Fine. If you don't have any doubts, we can proceed for next question. Can we proceed? Yeah. So this is another question. This question was given in GATE 2015 ECE set 2 for 1 mark. The question is, in the circuit shown, the average value of the voltage VAB in volts in the steady state condition is, okay. So we have an AC source here and a DC source here. So how to solve this? Generally in a circuit, if we have different sources, we have, suppose in general I'm telling, if we have multiple sources with different same frequency, let's say multiple DC sources or multiple sources with same frequency, then we can use nodal analysis, mesh analysis, or else any other theorems we can use, superposition theorem, like that we can use. But let us say in a circuit we have multiple sources we have, and at different frequencies, each source is operating at different frequency. Okay, then the most recommended method is superposition theorem. Okay, since different frequencies are there, at a different frequency for inductors and capacitors the impedances will change according to the frequency. So better to use the superposition theorem. So what we do here is we use superposition theorem, one source at a time we'll consider. Okay, so we know, right, superposition theorem in a linear circuit, when different sources are acting, we will consider one source and other sources we will deactivate. Current sources will be open circuited and voltage sources will be short circuited. So, and the overall response is sum of the individual responses, right? So we will first consider the AC source. When you consider the AC source, so we need to deactivate the DC source. So the DC source deactivating means short circuiting the DC source. Here voltage source rate, I'm just short circuiting. Fine. Something 5 pi sine 5000 t. Now what we want? We want voltage across capacitor, that is VAB1 we will say. Okay. Now if you see this, hope in the previous classes I discussed something that we can apply here. If you see this circuit, it is like a LTI system, right? If you see this circuit, it is like some LTI system, isn't it? So because we have resistors, in this we have resistors, inductors and capacitor, the elements are, so it is LTI system, we can say. All linear elements are there. Okay, now if you see here, let us say I'm just redrawing this like this. This is V input, here V output, an LTI system. This is an LTI system. Input you are giving some sinusoidal voltage, some Vm sine omega naught t, something like this. So what will be the output? We have discussed it, right? For an LTI system, okay, if I give some sinusoidal signal as input, okay, you will get the sinusoidal signal as output, but there is an amplification in the magnitude and some phase will be added, right? Let us say h of omega is the frequency response of the LTI system. Then at the input frequency at omega naught, you find the magnitude and phase of the system. So this magnitude is k, that will multiply the amplitude, and phase, this phase is phi, that will be added up. Okay, since our circuit is an LTI system, now the voltage across the capacitor, here the voltage across the capacitor also will get a sinusoidal signal. Maybe there will be increase in some amplitude and some phase will be added. So The voltage across the capacitor is a sinusoidal signal. But we know what is the in the question it is asked to find out the steady state condition, the average value. The average value of any sine or cosine signal is zero, right? Any sinusoidal signal average value is zero. I think that you know, because what is the average value? Average value is 1 by t integral 0 to t, that sine omega naught t, let us say some Vm sine omega naught t dt. Okay, over a complete cycle, if you consider the average is nothing but average value is nothing but what? Area over one cycle by the time period. Area is positive area, negative area will get cancelled. So average value will become zero, right? I think this you know, for any sinusoidal signal, average value is zero, right? Now, so since it is an LTI system, output is a sinusoidal signal, but what we want is average value. So we get VAB1 0 will get, right? VAB1 0 we get. Is that okay? Now second source will consider, DC source will consider, and the AC source again we will short it. Now you know at steady state, I think you have studied the transient analysis, right? Transients and DC transients. At steady state, you know, the capacitor acts as an open circuit and inductor acts as short circuit, right? In the DC transient analysis, okay, DC transient analysis you might have studied. At steady state, capacitor acts as open circuit and inductor acts as short circuit, and resistor as it is, it will not be affected. Okay. Now just I am drawing this. So anyway, the second for so second source DC source I am considering. So the AC source will be short circuited, resistor 1 kilo ohm, and capacitor acts as open circuit at steady state. So this is nothing but VAB2, and inductor acts as short circuit, right, at steady state. So this is the equivalent circuit at steady state when only 5 volt resist 5 volt voltage source is acting, right? Now the capacitor is general in steady state, the capacitor is completely charges to the source voltage. Again you can apply here some KVL, something you can apply here. What we get, VAB2, what we get is 5 volts, right? Steady state, what happens, the capacitor completely charges to the whatever voltage source present, DC source present. You can apply KCL here. So sorry, what to say, KVL here. So since here capacitor is open circuit, so current in the circuit is zero. Current in the circuit is zero. So voltage drop across resistances are zeros, 0 volts. Okay. Now anyway inductor is short circuit. Now entire voltage is dropped across the capacitor. So VAB2 is 5 volts. Okay. Now due to AC voltage, what we got, VAB is 0. Due to AC voltage, that is VAB1, we got 0 volts average voltage. Due to DC voltage VAB2, we got 5 volts. So overall is what? Overall VAB is what? VAB1 plus VAB2. So we get 5 volts. So answer for this is 5 volts. Is that okay? Any doubts from this? Okay. So any other Students are having any doubts on this? Generally, in doing analysis in networks, especially in AC analysis, when different frequencies are acting, let us say here DC source is there. Other in place of this DC source, we have some other source, like let us say 10 cos some 200 2000 T. Two frequencies are there, so we need to apply the superposition theorem. Okay, so average value are asking. So since in LTI system, so the response across any element is also a sinusoidal. Input is sinusoidal, the response also sinusoidal. Average value in a sinusoidal signal is 0. So that's why AC, due to AC here we are getting 0, and due to DC we are getting 5 volts. Fine. Yeah, Navneet, once again, the entire question you want me to explain? Navneet, the question, entire question. Okay. Yeah. So quickly, I'm just explaining. Here, if you see in this circuit, we need to find out the average value. We need to find out the average value across the capacitor. This one. Okay. Now we have two sources here, one AC source, one DC source. What we will do, we will consider one source at a time. Okay. First, I'm considering the DC source. When I consider the DC source, only 5 volts is present here, and the AC source I'm just short circuiting. Okay. Now at steady state we need to find out the average value. At steady state the DC transients you might have studied. At steady state the capacitor acts as open circuit and inductor acts as short circuit. At steady state only when 5 volts voltage source is acting. So this is the equivalent circuit. Okay, so capacitor acts as open circuit, so there is no current in the elements. I equal to 0, yes. Why I is 0 means here the capacitor acts as open circuit, right? At steady state for DC analysis, capacitor offers infinite resistance. Okay, what is the impedance of capacitor? 1 by j omega c. We'll try to understand like this. So at DC means omega is 0. That means impedance across capacitor is what? Infinite. Infinite means open circuit. You can understand in that way also. Inductor is j omega L. So omega, DC omega is 0. So it is like 0 impedance. It is like short circuit. Got it right? Since the capacitor is open circuit, we will have I0. So you apply KVL, you will get VAB to 5 volts. And now we will consider the AC source alone. So DC we will deactivate. Then AC source only if we consider it is an LTI system. Only linear elements are there, resistor, capacitor and inductor. So the response across any element, response across capacitor let us say, is also a sinusoidal signal. Input, since we are giving sinusoidal, the response also a sinusoidal signal. Okay. The average value of a sinusoidal signal is 0, because what is the average value definition? This is the definition, right? Area 1 by t integral 0 to t x of t dt. Area in one period by time period. Area is 0. Positive cycle, negative cycle area is 0. So average value is 0. Okay. So AC average value is 0. DC average value is 5. So total is 0 plus 5 volts. Okay. Fine. We'll move on to the next question. This question is given in GATE 2013 ECE set 1 for 2 marks. The question is, the following arrangement consists of an ideal transformer and an attenuator which attenuates by a factor of 0.8. Okay. And an AC voltage VWX1. This one. AC voltage of VWX1, this one. 100 volt is applied across WX to get an open circuit voltage VYZ1. Okay, when you are applying input voltage VWX1, you are getting output voltage VYZ1. Next, an AC voltage VYZ2 here. Next case, they are applying here. Then you will get input voltage this side as VWX2. First time you are applying input here, VYZ1 is output. Second time input is being applied here, output is like measured at the input side. Then in the question they are asking what is these ratios VYZ1 by VWX1 and VWX2 by VYZ2. What are the ratios in the question that is asked? Okay, so since it's a transformer, right, we need to little bit try to understand about the transformer. So let us say we have an ideal transformer. Okay, we have an ideal transformer with N1 terms at the primary and N2 terms in the secondary, and at the primary voltage is V1 and impedance at the primary is Zin, let us say, and current is I1 entering, and at the secondary we have connected some load, let us say ZL, and the voltage across secondary is, let us say, V2. Okay, and the current is, let us say, leaving current I2. Okay, we have primary with N1 terms and 2 terms in the secondary. V1 is voltage across primary and I1 is current entering into primary. V2 is voltage across secondary and I2 is current leaving from secondary. Then you might have seen this, right, for a transformer V2 by V1, okay, voltage across secondary by primary is equal to N2 by N1, and this is equal to I1 by I2. Okay, I1 by I2, V2 by V1 equal to N2 by N1, I1 by I2. Here the condition is I1 is the current leaving from the secondary. Suppose I2 is current leaving from the secondary. Suppose if I2 is something is given like this, let us say I2 is, let us say, current entering. In that case, we'll get a negative sign here. Okay, this is about an ideal transformer. Fine. Now, if you see here, we can get from here V2 I2 equal to V1 I1. Okay, from here cross multiply these two, V2 I2 equal to V1 I1. This is output power equal to input power. So the power will not change in the transformer, ideal transformer. It will not be wasted. Whatever power is giving at the input, the same power will be produced at the output. Okay, next also the relation between input impedance and load impedance or output impedance. Let us say for this, so Z in is what? At input side we can say V1 by I1, right? Now what is V1 is what? In terms of V2 I'll express. So V1 is what in terms of V2 from here, from this equation. V1 is N1 by N2 into V2. I1 is, I can express I1 as N2 by N1 into I2. So this I can write like V2 by I2 into N1 by N2 square. So V2 by I2 means what? ZL, output impedance. So this is nothing but ZL. So relation between input and output impedances are this one. Okay, Zin equal to n1 by n2 square into Zl. Okay, so no need to remember this input output impedance relation. Just this relation we can remember, v2 by v1 equal to n2 by n1 equal to i1 by i2. So in this way we can derive those things. Fine. Now come back to our problem. So come back to our problem. In the problem it is given what, when Vwx1 is given as input, the output is Vyz1. Now for this transformer, let us say this is V1, we will say, and this is V2. Voltage across primary is V1, voltage across secondary is V2. Then what is V2 by V1? Just now we have seen V2 by V1 equal to N2 by N1. So N2 is 1.25 by N1 is 1. So from here V2 is 1.25 into V1. Now since what is given in the question, it is given an attenuator which attenuates by factor of 0.8. That means for the attenuator, if you see what is the input for the attenuator is V2 and output of the attenuator is YZ. So from here we can write Vyz equal to 0.8 times of V2, right? For the attenuator, input of the attenuator is V2 and output of the attenuator is Vyz. So Vyz is 0.8 times of V2. So from here, so what we get, Vyz equal to 0.8 into V2 is 1.25 V1. So what we got here, Vyz equal to V1. Actually, what is V1? Our V1 is Vyz is nothing but Vyz1. Here they have given it when Vwx1 equal to 100 volts when we are giving. So V1 is nothing but Vwx1. So V1 is nothing but Vwx1. So in the question they were asking what is Vyz1 by Vwx1. When 100 volts is given, this also you'll get 100 volts. Okay. So we got the relation between Vyz and V1. So Vyz equal to V1. So when V1 is nothing but Vwx1, 100 volts is given, Vyz1 also 100 volts will get. So the first thing they have asked here, Vyz1 by Vwx1, that is 100 by 100. Now second case what they are asking, when Vyz to 100 volts is given. Now the next case is second case. Now some 100 volts is applied here. Vyz to 100 volts is applied here. Now what is the voltage here? They are asking. Let us say at that time Vwx2. The ratio they are asking. Okay. Since the transformer is a bilateral network, so when you are applying 100 volts input, output you are getting 100 volts. Previous case we have seen 100 volts when you are giving input, output you are getting 100 volts. Similarly at the secondary, if you apply 100 volts, we will get the same output at the primary also, 100 volts. Okay. So bilateral elements, primary and secondary, we can interchange in a transformer. So when I am applying 100 volts at primary, we got 100 volts at the secondary. Just now we have seen Vyz. In the similar way, 100 volts if I apply here, the same 100 volts will get at the input. So in that case also 100 by 100 will get Vwx2 by Vyz to 100 by 100. So option C is the correct answer. If you have any doubt, you can solve in the similar way. So this, let us say this is V2, then VYZ2 is, we have seen it, zero point 0.8 V2. So VYZ2 how much is given? 100 is given. So that is 100 by zero point 0.8 V2. I think this is 125. Okay. Now V1 we want in this case. So V2 by V1 equal to 1.25 by 1. So here V2 is nothing but V2 and V1 is VWX2. VWX2. This is since 125. So VWX2 also we will get 100. So we want the ratio VWX2 by VYZ2, 100 by 100. C is the option. Is that okay? Fine. I think it is time for the other session you have to attend. One more question is there, but it is already time. So I'll stop here and maybe in our next class, I think we will solve some problems from DTFT or DFT, those things, signals and systems. Before starting the next topic, I'll just solve one or two problems. After completing this, we will start signals and systems. Thank you all. Thank you very much. Okay, okay. Thank you, Mohan. Yes, thank you.